In the name of God, I'm Motahareh Dehghan. My paper title is Privacy Preserving Data Fusion Protocol. In IoT environments, a large amount of heterogeneous data is generated from different devices in a short time. In all applications of IoT, data quality is important in decision making. Data fusion is an approach to increase the quality of data collected from different sources and decrease the amount of wrong and conflicting data. Collecting data from different sources and fusing them has many benefits. However, there is concern about privacy violations for data owners. Designing a privacy-preserving protocol for data fusion is important. To the best of our knowledge, no protocol has been provided for private data fusion. In this paper, we proposed a private protocol for data fusion in IoT environments based on the Diffuse Method. The computational and communication complexity of our proposed protocol is in order of n. We proved the security of our proposed protocol based on the real idle simulation paradigm. Also, we consider the problem of achieving security in the presence of semi-honest parties and adversaries. Data fusion is the combination of data at a given time so that the data obtained from fusion is comprehensive and complete. And by using this data, different aspects of the environment are discovered and represented. Data obtained from the fusion process has more accuracy, integrity, and robustness than any of the separate data. Data fusion in distributed and heterogeneous environments such as IoT is challenging because this environment consists of heterogeneous systems that create data that has different fusion characteristics. This makes it difficult to analyze the relationships between different data. Even when the datasets are semantically related to each other. Scalability is another challenge for IoT due to frequent changes in the topology and size of networks. With the development of networks and cyber infrastructure, employing different types of security sensors for the detection of cyber attacks and mitigation of their impacts is growing. However, managing these devices encounters many problems, including overload and high false positive warnings. To solve these problems, many researchers have tried to use data fusion. The Dempster-Shafer theory is mainly used to process uncertain or non-accurate data without prior knowledge. However, there is an important challenge of privacy violations for data resources in IoT environments. Therefore, data owners have concern that their data will be disclosed during the process of data fusion. So far, the private protocol for data fusion has not been proposed. In this paper, we proposed a private protocol for data fusion in IoT environments based on the Diffuse method. In the Diffuse method, the combination of weighted evidence is used. In that method, the weight indicates the degree of trust that exists in a data source. The higher weight of evidence leads to a higher degree of reliability to them. In that case, higher weighted evidence will have a greater effect on data fusion. Diffuse is based on Dempster-Shafer theorem. The contextual parameters used in the diffuse method are the lifetime of sensed data, which is represented by weighted Dempster-Shafer method, and the distance between sensors and the entity, which is represented by weighted Dempster-Shafer method. Diffuse consists of four steps as shown in this figure. The first step in the diffuse method is the calculation of the credibility degree of evidence. To calculate the distance between two evidence sets that are collected by sensors, equation 1 is applied. And to calculate the credibility degree of each evidence, equation 4 is used. After calculating of credibility degree, it is necessary to calculate the uncertainty degree of evidence. Each evidence suffers from a degree of uncertainty that affects its involvement in the final combination. After calculating the uncertainty degree of evidence, there are three conditions. 1. Evidence with a high degree of uncertainty or low data volume that should be assigned a small weight. 2. Evidence that has a low degree of uncertainty and a significant distance from other evidence. 3. Evidence that has a low degree of uncertainty and low evidence distance should be assigned a high weight. Then the following two steps are used to calculate the information volume of sensed data for each evidence. First, equation 5 is employed to calculate the entropy of each evidence. Second, the distance between evidence and other sets of evidence should be measured. For this purpose, the distance between two evidences is computed and the furthest evidence is ignored. If the sum of intervals between the evidence reaches a certain threshold, the certainty is considered negative, otherwise it should be considered positive. Ultimately, the final weight for each evidence is calculated by using equation 6, where it is sums of all the evidence. In the field, several underlying parameters are taken into consideration, such as the distance between sensors and entities and the life of the sensed data. To measure the validity of data, a new parameter, WDST, is added. By using equation 5, the lifetime of sensed data is normalized as follows, where delta t demonstrates the maximum lifetime or total duration of data when all sensed data are recovered, and h shows the lifetime of observation, as provided by the equation 8. In equation 8, t is the current time and Tms is the time when SD was collected. The second parameter is distance between sensors and entities. In WDST, the resolution of space affects the quality of decision making. In that, decision making is influenced by the distance between the sensor and the monitored entity. Equation 9 illustrates the normalization function. ds and E is the distance between the sensor S and the entity E. The max shows the maximum distance to trust the sensor observations, and delta demonstrates the accuracy of the sensor that measured based on the statistical estimation. For each evidence I, the weight Wi is defined by the equation 10. Suppose that there is a set of evidence. The normalized weight is shown as equation 11. Then, weighted sets of evidence are combined using equation 12. In the diffuse method, 12 equations ultimately lead to the fusion of data with the mentioned requirements. Some of these equations are performed without communication and data transfer between data sources, which doesn't violate the privacy of data resources. In contrast, some equations require communication and data transfer, which may lead to data disclosure. This table summarizes how each of these equations is calculated. Based on the diffuse method, to fuse the data securely, we first need to calculate the distance between vectors of evidence generated by the data sources securely. It is necessary to calculate equation 1 securely and commonly between data sources. We expanded equation 1 and converted it to this equation, in which the scalar products between resources should be performed jointly and securely. In a secure scalar product of two vectors m1 and m2, each participant first receives two random values through a secure channel and from a trusted third party, so that the first party receives the random vector R1 and the numerical random value R3. Also, the second party receives the random vector R2 and the numerical random value R4 from trusted third party. Then each party sends the value, the vector of Vi, to the other party. V1 to the second party, V2 to the first party. They can calculate the scalar product based on the received values from the other party. After calculation of the distance between the support degree for each evidence should be calculated based on the distance and equation 3. In equation 3, the output of protocol 1 is used and it is performed locally and without any data transfer. Hence, each data resource calculates equation 3 locally. Then, based on the calculations, it is necessary to measure the credibility of each evidence based on equation 4. For this purpose, it is necessary to securely calculate the sum of the support degree for all evidence. We use an additive and multiplicative homomorphic encryption scheme, for example, the cryptographic scheme of Pallier. To secure the calculation of equations 4, 6, and 11, we use secure addition based on homomorphic encryption. We propose protocol 2 to calculate the secure addition between three parties, which can be generalized to coparties and can be used in the secure calculation of equations for 6 and 11. To calculate equation of 12, we use secure multiplication based on homomorphic encryption. The details of each are stated in Protocol 3. Other calculations are also performed locally. In this protocol, data sources securely combine their evidence. We use secure multiplication based on homomorphic encryption. For simplicity, we provide a protocol for 3 parties but can be generalized to k parties. Also, since the numerator and denominator of the fraction in this equation are similar, we provide the protocol for secure calculation of its numerator, which can be used for its denominator too. By performing calculations locally and proposing protocols 1, 2, and 3, each data sources can fuse their evidence while preventing the disclosure of their contents. Okay, to analyze the complexity of our proposed protocol, for example, we argue about the first protocol. In the first protocol, each participant receives a random vector and a random bit from a trusted third party. Assuming the vectors are n bit 2 and plus 2 bits are transferred. In phases 1 and 2, we have n-bit vector transitions that lead to 2n-bit transmissions. There is no data transfer in the third and fourth phases. In the fifth phase, the results of the calculations performed in phase 3 are transmitted. This result is numerical. If we display the calculated number with L bits in the fifth phase, L bits will be transferred. In phase 6, we do not have data transfer. Finally, in the seventh phase, the result of calculating the evidence distance, which is expressed numerically, is transmitted. Assuming that the output is L bits, in the phase L bits are transmitted. Thus, the number of bits transmitted in this protocol is 4n. Computationally, it is necessary to investigate the number of addition and multiplication operations. In phases 1 and 2, there are n addition operations. Each component in the vectors m1 and 2 are added together. In the third phase, it is necessary to perform n-1 addition operation to calculate the scalar product. Also, n multiplication operation and n-1 addition are required to calculate m2. Finally, we should add R3 with the output. In the fourth phase, a number of addition and multiplication operations is similar to the third phase. In the fifth phase, a multiplication operation and an addition operation are required. In the sixth phase, two multiplication operation and two addition operations are required. A squared action is also required. If we consider this operation as a modular exponential, the computation complexity of this operation is in order of n. Okay, in conclusion, We state that data fusion is an approach to increase the quality of data collected from different sources and decreases the amount of wrong and conflicting data. Collecting data from different sources and fusing them has many benefits. However, there is concern about privacy violations for data owners. Designing privacy-preserving protocol for data fusion is important. In this paper, we propose a private protocol for data fusion in IoT environments based on the Diffuse Method. The computational and communication complexity of our proposed protocol is in order of n. We prove the security of our proposed protocol based on the real ideal simulation paradigm. Also, we considered the problem of achieving security in the presence of semi-honest parties and adversaries. So, design of a secure information fusion protocol that is secure against malicious adversaries is of interest. Thank you very much.